Hello everyone. In this video, we are going to discuss about Kossel Lewis approach to chemical bonding. Please excuse me for the pronunciation. See, this is of the topic from the chapter Chemical Bonding and Molecular Structure, which is chapter 4, class 11, Chemistry. So you see, when we talk about this Kossel Lewis approach to chemical bonding, first of all, we want to know about what is a molecule as well as a chemical bond. See, matter is made up of one or different types of elements. Under normal conditions, no other element exists as an independent atom in nature, except the noble gases. However, a group of atoms is found to exist together as one species having characteristic properties. Such a group of atoms is actually called as a molecule. We have, for example, hydrogen molecule H2. See, two hydrogen atoms are there. So, a group of atom, that is a molecule. When you consider water molecule H2O, see a group of atoms. Two hydrogen atoms and one oxygen atom. So, a group of atoms are there. So, that is a molecule. Okay, so a group of atoms, that is actually called as a molecule. See, there must be some force which holds these constituent atoms together in the molecule. That is, when you consider water molecule, there are two hydrogen atoms and one oxygen atom. So, there must be something. There must be some force which holds or which, binds all the three atoms together to form a water molecule. So, the attractive force which holds these constituents, various constituents, atoms, ions, etc. together in different chemical species, that is actually called as a chemical bond. The attractive force which holds various constituents means atoms, ions, etc. together in different chemical species, that is actually called as a chemical bond. See, in order to explain the formation of a chemical bond in terms of electrons, a number of attempts were made. Kossel, and Lewis, they succeeded independently in giving a satisfactory explanation. Lewis, he proposed a cubical atom model in 1916 which described the atom's structure using a kernel and outer shell. See, kernel, it is actually the positively charged core consisting of nucleus plus the inner electrons. In the nucleus, we have the positively charged protons and neutral neutrons. Then these, for example, if you consider the sodium, its atomic number is 11. So, electronic configuration will be 281. Okay, so the first shell we have 2 electrons. In the next shell we have 8 electrons. In the outer shell we have 1 electron. So, this positively charged core plus these inner electrons. So, you see these are inner electrons and this is the outer electron. So, the positively charged core plus these inner electrons together, that is actually called as a kernel. Then, outer shell, it actually surrounds the kernel and could accommodate a maximum of 8 electrons. In the case of sodium, only 1 electron is there, but it can accommodate a maximum of 8 electrons. Now, when we come to this topic, cubical arrangement, Lewis assumed that the outer shell electrons occupy the corners of a cube surrounding the kernel. That is, for example, if you consider a sodium, its atomic number is 11. So, electronic configuration will be 1s2, 2s2, 2p6, 3s1. That is 2 plus 6, 8 electrons, 1 electron. 2, 8, 1, that is the electronic configuration. So, for sodium, you see only 1 electron is there in the outer shell. Only 1 outer shell electron is there for sodium. Okay, so this single outer shell electron of sodium would occupy one corner of the cube. So, here I have just drawn a cube. Let us consider this green colored one as the kernel. Okay, now the outer shell electron will occupy the corner, okay, of the cube surrounding this kernel. So, the outer shell electron, only 1 electron is there. So, that will be at one of the corners of this cube. There are 8 corners for a cube now. So at one end of the one corner of the cube, there will be the outer shell electron as per this cubical arrangement of Lewis. Okay, similarly, in the case of a noble gas, for example, you see when you consider a noble gas, all the 8 corners of the cube would be occupied. For example, if you consider neon, its atomic number is 10. So, electronic configuration 1s2, 2s2, 2p6. That is 2, 8. That will be the electronic configuration. So, in the outer shell, there are 8 electrons. Okay, so when we use this cubical arrangement, all the 8 corners of this cube would be occupied because there are 8 electrons in the outer shell for neon. Okay. See, Lewis postulated that atoms achieve the stable octet. Octet means 8 electrons in the outer shell. So, Lewis postulated that atoms achieve the stable octet when they are linked by chemical bonds. For example, let us consider the sodium atom whose atomic number is 11. So, electronic configuration 281. For chlorine, atomic number is 17. So, electronic configuration 287. Okay, now when you consider the molecule NaCl, that is in the case of sodium chloride NaCl molecule, transfer of one electron will take place from sodium to chlorine. Because you see, sodium has one electron in the outer shell. So to make or to achieve the stable octet, it will tend to lose its one electron. And sodium will become Na plus ion by losing this one electron. Okay, so you see, for sodium, its electronic configuration is 281, which is not a stable configuration. For stable configuration, the outermost shell should have 8 electrons. So what it will try to do? It will try to lose this one electron. So after losing this one electron, this sodium will become Na plus 1 electron. That is, 1 electron is lost from us. So Na plus means 1 electron is less. Okay, that is now its electronic configuration is 2, 8 for Na plus, and it achieved the stable octet. Okay, similarly, this chlorine has 7 electrons in the outer shell. So to achieve the stable octet, 8 electrons, it will try to gain an electron. So chlorine will try to gain this electron lost by sodium. See, chlorine has 287 electronic configuration. When it accepts this electron, it becomes Cl minus ion. So, what about its electronic configuration for Cl minus ion? 2, 8. Already 7 electrons were there. It accepted 1 electron more. So, now it is 8. 2, 8, 8. So, it achieved a stable octet. Okay. So, you see, when sodium loses 1 electron, it becomes Na plus ion. And chlorine accepts that 1 electron. This 1 electron is accepted by the chlorine atom and it becomes Cl minus ion. In this process, each atom attains a stable octet. That is, a stable octet means 8 electrons in the outer shell. Now, let us discuss about Lewis simples. In the formation of a molecule, only the outer shell electrons take part in the chemical combination and they are known as valence electrons. Valence electrons. The inner shell electrons are well protected and are generally not involved in the combination process. An American chemist, G.N. Lewis, introduced simple notations to represent valence electrons in an atom. These notations are called Lewis simples. For example, let us consider the second period elements lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine and neon. See, for lithium, its electronic configuration is 2,1 because its atomic number is 3. So, the outermost electron is only 1 electron is there in the outer shell. So, the Lewis simple for lithium is this is the Lewis simple for lithium. That is, it's simple Li with a dot. See, this dot actually represents the electrons in the outer shell. Only one electron is there in the outer shell, so only one dot. Okay, similarly, if you consider beryllium, its atomic number is 4. So electronic configuration 2, 2, outer shell electron is 2, so 2 dots. Okay, so for boron, its atomic number is 5, so electronic configuration 2, 3, outer shell electron 3, so 3 dots around B. For carbon, its electronic configuration is 2, 4 because its atomic number is 6. So the outer shell electron is 4, so 4 dots around C. Okay, these are the Lewis simples. Similarly, if you consider fluorine, atomic number 9, so electronic configuration 2, 7, 7 electrons are there in the outer shell. So you see 2, 4, 6, 7, 7 dots are there around F. Similarly, for neon, atomic number 10, electronic configuration 2, 8, so outermost electron number is 8, so 8 dots are there around Ne. So you see these are actually the Lewis simples. Okay. Now, let us see the significance of Lewis simples. The number of dots around the simple actually represents the number of valence electrons. So, when you consider oxygen, this is the Lewis symbol for oxygen. How many dots are there around this letter O? 2, 4, 6. So, number of dots around the symbol O that actually represents the number of valence electrons. That is, number of valence electrons for oxygen atom is equal to 6. Okay, this number of valence electrons helps to calculate the common or group valence of the element. See, valence electrons means the number of electrons in an atom, atom's valence shell or outermost energy shell. That is number of dots around the symbol. See, group valence, which is also known as the common valence, valence or typical valence of an element. It actually represents the number of electrons in an atom, typically gains or loses or shares to form chemical bonds. The group valence of the elements, that is generally either equal to the number of dots in the Lewis symbol or 8 minus the number of dots or valence electrons. Number of dots that is actually equal to the valence electrons. Okay. That is, for example, let us consider the group 1 element, which is sodium. Its atomic number is 11. So, electronic configuration 281. So, its Lewis symbol will be what? Na. Outermost shell only has 1 electron. So, Na. This is the Lewis symbol for sodium. Now, what about the number of valence electron? Number of valence electrons, that is actually equal to the number of dots, that is 1. And what about the group valence of sodium? Group valence, that is either equal to the number of dots or 8 minus number of dots. Here this is equal to the number of dots, that is equal to 1. Okay, now if you consider another element, group 15 element, which is nitrogen. Its atomic number is 7. So you see this is the Lewis symbol for nitrogen. What about the number of valence electrons? Number of valence electrons, that is actually equal to the number of dots around the symbol, that is 5. Okay, now its group valence, that is sometimes it will be equal to the number of dots, that is number of valence electrons. Sometimes it will be equal to the 8 minus number of dots. So in the case of sodium, it is equal to the number of electrons, number of valence electrons or number of dots. But for nitrogen, its number of valence electrons is equal to 5. So its group valence or common valence or typical valence, that is actually 8 minus 5. Typically it is 8 minus 5, which is equal to 3. Okay. Now let us see the Kossel's observations. It actually highlighted the key aspects of chemical bonding. In the periodic table, the highly electronegative halogens and highly positive alkali metals, they are separated by the noble gases. That is, the noble gases act as a divide between electron donors, that is alkali metals, which is on the left side of the periodic table, and electron acceptors, which are the halogens, which are on the right side of the periodic table. Now the next observation is the formation of a negative ion from a halogen atom and a positive ion from a alkali metal atom that is associated with the gain and loss of an electron by the respective atoms. That is, highly electronegative halogens, group 17 elements, they tend to gain electrons and form a negative ion. Highly electropositive alkali metals, group 1 elements, they tend to lose electrons and form a positive ion. The third observation is the negative and positive ions thus formed attain stable noble gas electronic configurations. The noble gases have a particularly stable outer shell electronic configuration of 8 electrons, that is called as octet, with the exception of helium which has a duplet of electrons. Duplet means 2 electrons. Octet means 8 electrons. So, helium, which is considered as a noble gas, but it has only 2 electrons, that is duplet of electrons in its outer shell. But all other noble gases have octet of electrons. Okay, 8 electrons in the outer shell. So, the negative and positive ions formed attain a stable noble gas electronic configuration. That is, for example, if you consider sodium, its atomic number is 11. So, electronic configuration is 2, 8, 1. When it loses this 1 electron, it becomes Na plus ion, that is sodium plus, positive ion. Now, Na plus has an electronic configuration which is 2, 8. 1 electron is lost, so 2, 8 only. So, outermost shell has 8 electrons now for sodium ion, which is a stable configuration. Okay, similarly, when you consider fluorine, its atomic number is 9. So, its electronic configuration is 2, 7. So, to achieve a stable electronic configuration, that is to make its outer shell 8 electrons, it will accept 1 electron, it will gain 1 electron, and it becomes a negative ion, F minus ion, fluorine ion. This F minus ion has an electronic configuration now 2. It was 7, but it gained 1 electron, so 2, 8. So, outer shell has 8 electrons, octet of electrons, which is a stable configuration. So, the positive ions and negative ions, they attain a stable noble gas configuration. That was the third observation. Now, let us see the fourth observation. The negative and positive ions are stabilized by electrostatic attraction. That is, oppositely charged ions, positive and negative ions, they are oppositely charged. They attract each other. For example, if you consider Na plus and Cl minus ions, they are oppositely charged. So, there will be an electrostatic force of attraction between them. This electrostatic attraction holds the ions together. And it forms what? NaCl, sodium chloride. Okay, so the negative and positive ions, they attract each other. The electrostatic attraction holds the ions together. The attraction between cations, that is positive ions, and anions, that is negative ions, forms a strong ionic bond between the atoms. For example, let us see the formation of sodium chloride NaCl from sodium and chlorine. See, we know that sodium, which has an atomic number 11, okay, its electronic configuration is 281. So, to achieve a stable electronic configuration, it will lose 1 electron and it will become Na plus ion. See, this Na plus ion has an electronic configuration 2,8, which is a stable configuration. Okay, now the chlorine atom, which actually has 17 electrons, atomic number 17, so electronic configuration 287. This will accept or gain this electron and it will become Cl minus ion. Okay, when you consider this Cl minus ion, it has an electron configuration 2, 8. It was 7, it gained 1 electron, so now it is 2, 8, 8, which is also a stable electronic configuration. Okay, now you see, now the outputs are actually this Na plus ion and this Cl minus ions. These are oppositely charged ions. They attract each other and they form the NaCl, which is the table salt. That is, Na plus and Cl minus joins together and form Na plus Cl minus or NaCl, which is the table salt. Now, let us see the formation of CaF2. See, for calcium, its atomic number is 20. So, its electronic configuration is actually 2882. Okay, because for calcium, electronic configuration will be like 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. So, 2 plus 6, 8. Here 3s2, 3p6. So, again 8. 4s2. So, 2, 8, 8, 2. That is the electronic configuration for calcium. So, it will become Ca2 plus ion by losing 2 electrons to achieve a stable electronic configuration. Okay, similarly, because when you lose 2 electrons, for Ca2 plus, its electronic configuration will become 2, 8, 8. So, it achieves an octet, 8 electrons in the outer shell, stable configuration. Okay, now CaF2, no? So, when you consider one fluorine atom, its atomic number is 9, so electronic configuration 2, 7. One fluorine atom will gain 1 electron and it will become F minus ion. When you consider F minus ion, its electronic configuration will be 2, 8 because it was 2, 7, it gained 1 electron, so 2, 8. There are 2 fluorine atoms. So, the second fluorine atom that will also gain, actually there are 2 electrons lost by calcium. So, 1 electron is gained by one fluorine atom, the another electron will be gained by another fluorine atom and it also will become F minus ion. So, together we can write 2 fluorine atoms, they gain 2 electrons and becomes 2. So, we have Ca2 plus ion here. Okay, then there is 2F minus ion here. Both are oppositely charged. So, there will be an electrostatic force of attraction between them. So, they combine together and will form Ca2 plus F minus twice. That is CaF2. Okay, the attractive force which holds the Ca2 plus ion and F minus ions in this is generally termed as a chemical bond. The bond formed here is as a result of the electrostatic attraction between the positive and negative ions, and that is termed as an ionic bond or electrovalent bond. So, the bond formed as a result of electrostatic attraction between the positive ions and negative ions, that is actually termed as an electrovalent bond or ionic bond. See, electrovalence, that is actually equal to the number of charges on the, number of unit charges on the ion. For example, for calcium Ca2 plus, its electrovalence will be, you see, plus 2. For Cl minus, its electrovalence is minus 1. Minus means this is minus 1. Okay, now you see, Kossel's postulations provided the basis for the ion formation and formation of ionic crystalline compounds. At the same time, he did recognize the fact that a large number of compounds did not fit into these concepts. Now, let us discuss about the octet rule. Kossel and Lewis in 1916 developed an important theory of chemical combination between atoms known as electronic theory of chemical bonding. According to this, atoms can combine either by transfer of valence electrons from one atom to another, that is gaining or losing, just like we seen in the case of NaCl, CaF2, etc., or by sharing the valence electrons in order to have an octet in their valence shells. That is actually known as octet rule. That is, atoms can combine either by transfer of valence electrons from one atom to another by gaining or losing it, or just like we seen in the case of sodium chloride, or by sharing the valence electrons in order to have an octet 8 electrons in their valence shells. That is actually known as octet rule. That is, this rule states that atoms tend to gain or lose or share electrons to achieve a stable electronic configuration with 8 electrons in their outermost energy level or valence shell. So Na becomes Na plus 1 electron, it becomes Na plus by losing 1 electron to achieve 8 electrons in its outermost energy level. See, sharing of electrons to achieve the 8 electrons in the outermost shell, that will be discussed in the next video when we are discussing about covalent bond. So I hope it is clear to you. Thank you.